tell me when to start. Why don't you give a little introduction to your group and say who you are, what you're doing?
Sure. We are here in Regina, Saskatchewan, Canada, and we are just gathered as a small group of science teachers that are hoping to dig deeper in some concepts, and we are looking for things that we can share with our students and just have a deeper understanding. So we look forward to your presentation.
Okay, excellent. And so let me begin by saying good morning to all those in Saskatchewan, and good evening to the few people who are over here in Islamabad. We're bridging continents. We're almost 12 hours apart from each other. Okay, so I want to talk about fields in physics. And these will be of two different kinds. Classical physics, the classical fields that you encounter, and I'll give you lots of different examples, and the much more recent idea of quantum fields, which lies at the very heart of modern physics. So let me first of all put before you the agenda that I will be following. So here's an outline. I thought I'd make a systematic outline because this is going to be quite a spread of topics. I'm going to start with talking about how the idea of a field came about in Newtonian mechanics. And this is critically related to how fast information can travel. This will lead us to a proper definition of what a field is. It'll turn out to be very simple, actually. But then there are very different kinds of fields. There are scalar fields, I'll give you examples, vector fields, and also other kinds of fields that I won't talk about, but if somebody is really curious, I will. And then I'll give examples of electric, magnetic, and the electromagnetic field, which is quite interesting because it's one is not very different from the other. That will be basically what I'll talk about in the context of classical fields, and then I'll go on to talk about quantum fields. But before I can talk about quantum fields, I have to tell you a little bit about what quantum mechanics is. Quantum field theory. So let's have a bit of a historical background on this. Quantum mechanics started in the 1920s. The idea of the quantum field theory came about a decade later, and I'll tell you a little bit about that. What's the difference between classical and quantum fields? We'll discuss that. And then you often hear of the electron field, the quark field, the photon field, the Higgs field. How is that related to the idea of particles? The relation between fields and particles is something that is often not clear, and so I'll be discussing that. Then I'll talk about the quantized electromagnetic field. Now, every field can be quantized, but the quantized electromagnetic field is particularly important. Then I'll take you on a little tour of particle physics, and it'll be very elementary, and there'll be names that are strange over there. And then towards the end, I'll talk about what is called the God particle. It's a very bad name. I'll tell you why it's a bad name, but it's something that has captured the imagination of so many people, and associated with that is a field. Now, at the very end, I'm going to talk about how that Higgs field could perhaps lead to the universe ending very suddenly. Now that's of course very speculative, and we hope it will not end, but these are really nice things to discuss. Okay, so let's start with the whole notion of how people found it necessary to talk about fields. If we go back to Newton's times, Newton, while discussing his law of gravitation, said that the force between two masses is the mass of one times the mass of the other divided by the square of the distance. So if I put one mass here, another mass there, they will attract each other with force that's equal to what you see on the board. That's Newton's law of gravitation, the inverse square law. And it says that if I pull them apart, the force will get weaker, the attraction will get weaker. But then suppose I do the following. This mass, I make it suddenly disappear, or if I can't do that, I move it away extremely fast. So I jerk it from here to here. Will the force be that? 1 over, that is to say, proportional to 1 over the square of the distance, or what? I mean, this is called action at a distance. The assumption in Newton's time was that this force was instantaneous. But actually, we know it is not. So, for example, if the sun, so there's the earth which is going around the sun, and if the sun were to suddenly disappear, we wouldn't know until 8 minutes later. Okay, so that's a clear violation of Newton's law of gravity. And so then the notion of a gravitational field appeared. Now let me give you another instance of this. So imagine that there's a charge over here and there's a charge over there, and let's say they're the same charges, both positive. Then they'll feel repulsion between the charges. And now, of course, that is Coulomb's law. Now, if I suddenly move this up, how long before that information is transmitted over here? If one was to believe Coulomb, just like one was to believe Newton, in zero time. But we know that light takes a while to go from here to here, a very small amount of time, but nevertheless a finite amount of time. So that is where the idea of a field originated from. Now let's go and have a quick review of the idea of a field. Okay, a field is really, I'm going to define it now. A field is something which is a function of distance and maybe of time and maybe of both. So let me now give you a few examples of fields and also tell you of the different kinds of fields. So let's have a look at these slides over here. Here's an example of a scalar field, and this is the atmospheric pressure. Now, if you go to the top of a building, the pressure over there is less than what is at the bottom. If you go, as you go higher and higher up, if you fly in an aeroplane, the pressure is far less. That's why you need to pressurize the cabins. You go still further, well, of course, the pressure becomes less and less. The point is that the atmospheric pressure, oops, sorry, I missed that. Okay, so the atmospheric pressure is a scalar field. That means it has no direction. Of course, you might say, but pressure is force per unit area, and force is a vector, so why am I talking about this? Well, if you take a fluid or you take air, then if you take any one point, the pressure, the force acting here in this direction, in this direction, in this direction, in this direction, they're all the same. And so there's no direction to pressure. It's a scalar quantity, it's a number. You say it's 1 atmosphere down here and half an atmosphere and then a third and a tenth or whatever. Another example. As I speak to you, my mouth is creating pressure waves. It is creating density waves, you could say. So, as you can see over here, this is a loudspeaker. The particles bunch up over here. There's more density, more particles per unit volume here as compared to here. Again, it goes up, down, like over here in this sine wave below. You could mathematically represent this as a function of two variables. The distance from the loudspeaker, which will be x, and of course the time t. As you stand in one place, the pressure will go up and down. It will oscillate sinusoidally if there's a pure wave coming towards you. And that's again an example of a classical scalar field. So it's just a mathematical function of x and t. Another example. So I have a string and it's, I have two strings over here, and they are taut between these two wedges over here. If I pull one of these strings, well, then it can go up and down, and it'll oscillate up and down, and the distance it goes up at a given time t, we would call that the displacement field of the string at distance x from one end at a time t. So that's an example of a displacement field. Okay, now let's come to a vector field. Now you all know that if there's a positive charge, then from this positive charge there will be field lines that will be coming out. If it's a negative charge, the field lines will be coming in. Now what does that mean? That means that if I was to put over here a unit charge, a unit positive charge, it would feel a force in the direction of this field line over here. And it would feel the opposite, it would feel an attractive force towards this center over here where there's a negative charge. If I have a positive charge and a negative charge, well, then again, what we will do is we will add up two vectors. So here is an electric field. I've put a little arrow on top. It's at a particular x, y, and z. And if these charges are fixed, then of course there's not going to be any time dependence. So this is what we would call a static electric field, a stationary electric field. So I guess that's pretty simple. Here is a bar magnet, and the bar magnet is surrounded by iron filings, and we could, well, take a little compass around the bar magnet, and at any position, say over here, see this red dot over here, the compass would be pointing along the direction of the magnetic field vector. So you see there's a direction for the magnetic field. It's different at different points, And so this is a vector field. A vector field meaning it's got three possible directions in which it can point, and its strength will be different at different points. Pretty simple, nothing very complicated over here. But now let's get into something more interesting. That's the electromagnetic wave. The electromagnetic wave has got both a magnetic field and an electric field. And if you were to stand at one point and you had something that measures the electric field, well, if the wave was going in one direction, you would see that, so if it's going in this direction, the x direction, the magnetic field would be in the y direction, the electric field would be in the z direction, perpendicular to each other, and they'd be increasing and decreasing with time and also changing with different points where you are standing. So x, y, z would be where you are standing, and it'll be different. The magnetic field and the electric field will be different at a given time depending on where you are located. So here is a situation where you have both an electric and a magnetic field, and both are changing with position and time. Okay, so now here is the question. Here is the question. In the case of a sound wave, you needed a medium. The medium was air. Of course, sound can travel through iron as well. Sound travels through the earth as well. See, if I hit something on the ground over here, the waves will travel to the other end of the earth. They'll get weaker as they go along, but they'll be propagating with some speed. So all these are examples of where a wave travels through a medium, but hey, the light from the sun, it reaches us. What's the medium over there? So let's go back 200 years. The idea was at that time, because see, physics is basically learning from experience. Our experience told us that sound needs a medium to travel through. So light needs a medium to travel through, and so the idea was that maybe there's something out there in space which we can't see, which we can't feel, but which is there, and they gave it the name ether. Well, the Americans spell it without the A, but it's the same thing. It's something that has no mass, can't be felt, but it was supposed to be there. Okay, so when Maxwell wrote down his equation, and this is 200 years ago, and told us that light is in fact electromagnetic waves, electric and magnetic waves, he had in his mind that maybe there's something like the ether over there. Okay, so then somebody said, hang on, should we not try and look for that? And so now I'll come to what is perhaps the most important failed experiment in modern history, done by two Americans, Michelson and Morley, and they did that experiment in 1881. They both got the Nobel Prize for it. And here was the idea. So if there is an ether, well, then it's that ether which conveys the light from the sun to the earth. Now the sun goes around, the earth goes around the sun, which means it's going through the ether. And suppose you stand on the earth, well, then there's a wind, an ether wind, which is blowing towards you. This is just like if you're in a car or a motorbike, okay? Motorbike is better, no windshield. The air is coming towards you, and if you will, the faster you move, the faster will be the wind. Okay, now remember, the sound, not the sound, the light from the sun is traveling through the ether towards the earth. Today, it is traveling, the earth is traveling in this direction. 6 months later, it's traveling in that direction. And so the speed that we would measure of the light would be different now as compared to 6 months later. In fact, even over one day, it's different because the earth is also spinning around. So it's 24 hours, 12 hours later, yeah. There would be the earth where we are would be going in the opposite direction as compared to the previous. Okay, to summarize this point, there's a spinning and rotating earth, and we are moving through a fixed ether. So the ether is like, the ether is not like, the ether is an inertial frame, a fixed inertial frame, which fills all of space, inside the solar system, outside the solar system, whatever. And so we should be able to feel that ether wind, just like a motorcyclist feels that wind coming towards him or her. And by the way, the speed of the earth is not small. It's something like 1/10,000th of the speed of light. Now you'll say 1/10,000th is a small number, but it's not. The speed of light is enormous. So this is something that should be seen if you can have a delicate enough experiment, and they made what is called an interferometer. Looking for that ether, they found none. And so this is why I've called it the most important failed physics experiment. Okay, now let me come to something that I am going to talk about in considerable detail at a later point, but you all know what waves are. Waves are periodic motions that have no beginning and no end. And so if you were to look at a wave from let's say, if you were to look at ripples, waves in the sea from a plane up there, you'd see the waves without a beginning, without an end. Of course, you know, with our Earth is finite, so you would see a beginning and an end, but an ideal wave never starts, never ends. So that's on the one hand. On the other hand, something like this is an object, and it's finite. It starts here, it ends here. It's finite. Now I'm going to explicate this point because many of you have heard of de Broglie waves, and you've always wondered, what have waves got to do with particles? So I'm going to make this point clearer, and talk a little bit about waves and bunches. As I said, a wave is something that repeats endlessly, has no beginning, no end. A bunch is something that is very finite. And now the interesting thing is that every bunch can be thought of as a sum of waves. You know, this is not something that would come naturally to somebody's attention, or, I mean, it took a mathematician like Fourier to understand this. And I'm not going to do Fourier analysis, but I will want to show you something that can be very easily understood using Mathematica. Okay, so Mathematica is a program that does all sorts of nice things. Now here, I will ask Mathematica to plot the function cosine of x. Everyone knows what cosine of x looks like. It just goes on and on. And so if I do that and ask it to calculate, ask it to plot, well, here is what the plot then looks like. It has no beginning, no end. Of course, I asked it to plot only in a little range, but it can just keep going on and on. Okay, now what I will do is I will ask it to add 5 different cosines. Now this is cosine of x, cosine of 2x, cosine of 3x, cosine of 4x, cosine of 5x. And just to make life simpler for Mathematica, I am dividing by 5. Why am I dividing by 5? Because at x equal to 0, this is 1, this is all of, there are 5 ones over here, and so at x equal to 0, I will have 5 over 5, which is 1. Right, now I am, so what am I doing? I'm adding up different frequencies of a periodic function, something that has no beginning and no end. But now let me see what that produces. I'm just going to resize this a little bit so that it's nicer looking. Yeah. So you see, now bunching is happening. First there was, the wave was spread over all space. Now I've added together 5 waves and I get something that's bunched up. So those of you, and by the way, we're talking to Canadian teachers, just to let people over here know that this is primarily addressed towards them. So what we're doing here is adding up cosines. We could have added up sines too, and in fact, we can get any shape by adding up cosines and sines with different numbers in front, say 0.5 over here, 0.3 over here, etc. Any shape can be obtained that way. Okay, now one last thing over here. You know, I could only write 5 terms because I got tired writing more terms than that, typing in. But now I can ask Mathematica to add up 100 terms. So the instruction is add up or sum cosine of nx, where n goes from 1 all the way up till 100, and then divide by 100. Mathematica will take just a tiny fraction of a second to do that and then to plot it, and here is what the plot looks like. Let me make this a bit bigger, and here, yeah, you see, and if I For those who know what I am talking about, if I was to add up an infinite number of these cosines, I would get what is called a delta function. But don't worry about that. Okay, so I hope I've convinced you that that adding up periodic waves then leads us to particles. At this point, I want to now get back to my PPTs. So, what we've done is basically the first part, classical fields. If there are questions, I'd be happy to take them at this point, because the next thing that I'll go on to is quantum fields. So, let me know if you have any questions.
Everything's sounding great. We're ready to keep going.
Okay, okay. So there's a question over here. Let me take that. Okay, just yeah. What's your question?
Sir, why was there only a single bunch? In all cases, we have seen a single bunch.
Oh, what I'm saying is that if you add up a whole number of sine waves or cosine waves, then you'll get something that's bunched up. You can every bunch can be expanded in terms of periodic functions. Okay, so next we will go on to onto quantum fields, and here's the agenda. I'm going to talk about the quantum mechanics of particles. We need to have at least some understanding of what quantum mechanics is, the quantum mechanics of particles, before we can go on to the quantum mechanics of fields. So let's do that. Now, the most weird thing about quantum mechanics is that, contrary to what is in our daily experience, where we see a particle and say a cricket ball, we know it's here and it's moving with this speed. We can measure both the position and the speed, or equivalently the position and the momentum of a cricket ball. But if one was to talk about something that's as small as an electron, then knowing the velocity and the position of that electron together, meaning at the same time, simultaneously, then that is impossible. And this was the absolutely revolutionary idea put forward by Heisenberg in 1927, and which is mathematically expressed as this: delta x, which is the uncertainty in the position of the electron, delta p, which is the uncertainty in its momentum, the product of the two is a small number, a very, very small number, which is called Planck's constant. There's a long history about that, but let's say that this is a number, just a number which, for no good reason, is very, very small. If we were in a different universe, it would be a larger number. Then we would see the weird things of quantum mechanics in our daily lives. Associated with that is the energy-time uncertainty principle, and actually they're not quite the same, and you can't get this from this, but you can, it has a different origin. That's technical, I don't want to get into that, but the consequences of these two uncertainty principles enunciated by Heisenberg in 1927 are just astonishing. Well, for example, according to the uncertainty principle, delta x, delta p is about h, this ball can never be at rest. So suppose that there's some curve like this, and there's a ball that can roll up and down, and it's our daily experience, or it's something that at least you can imagine very well, that if I put a ball, it'll go up and down depending on how high I have initially moved it. But if I put it at rest, at the bottom it'll stay there at rest. But, says Heisenberg, that's impossible. Because if I put it at the origin, that means it's definitely at a point x equal to 0. Which means there's no uncertainty in where it is, and that means that 0 times something is a finite number. Small, okay, but finite, and that's not possible. Which means that this ball will keep going up and down like that, and that is called 0-point motion. Now, I want to talk a little bit about this and actually show that the uncertainty principle leads us into actual predictions. And so let's so we're taking this ball over here, and the energy of this ball is its kinetic energy, which is the square of the momentum divided by twice its mass, plus the higher it goes, the more potential energy it has, and so it's let's call this thing, this height over here, or let's call the potential half kx squared x. So x would be the height above. Now, according to Heisenberg, this p is uncertain by an amount delta p, and that is approximately h bar over the uncertainty in its position delta x. And look, I'm not going to worry about whether this is p or delta p, and I'm not going to worry about whether this is x or delta x. What I see over here is that E then becomes, roughly speaking, h bar squared over 2m delta x squared. So delta p squared is h bar squared over delta x squared divided by 2m plus half k. And there's uncertainty in position. Okay, now you see that if delta x is very small, then this is going to be huge. And that means my energy will be very, very large. On the other hand, if delta x is very big, then this is going to be huge, and this will be very small. So there's going to be a trade-off between the kinetic energy and the potential energy. How is it that I can get the minimum possible amount of energy? Well, what I should do is then differentiate this energy with respect to delta x, and then I'll put it equal to 0. Well, once I differentiate this, I get minus h bar squared over 2m delta x cubed. See, delta x to the minus 2, when I differentiate that, I get minus 2, which then cancels this, and then there'll be this. And once I differentiate this, I get, again, the 2 will cancel this, and so I'll get k delta x. And now, if I put this equal to 0, see, the minimum energy will happen when dE by dx is equal to 0. Then from here, I get delta x, k delta x is equal to h bar squared over m, over km. Okay, so from here, so this is telling me that delta x is just right to minimize the energy. Well, we can, so if you could, you could also write this as h bar squared over m k to the power 1/4. But this is good enough. We found the right amount of uncertainty in the position. Okay, so what does this mean in terms of the energy? Let me write the minimum energy then, E, will be, this is delta, this is over here, minus h bar squared over m delta x to the 4 delta x, let me write it as that, plus half k delta x squared. And so now I can put in delta x over here and get that amount of energy. Let's see how much this works out to. Well, I'll leave it as that. The answer you can go out and work out for yourself. So the point over here was that this will keep oscillating back and forth, and there's no apparent reason for that other than the uncertainty principle. The uncertainty principle forbids the particle from being at rest. Let's take this other weird thing about quantum mechanics, and here okay, so here is something that you've seen. It's a train which is going through a tunnel. It's going through a tunnel because the train wants to go to the other side, and so instead of going up the mountain, there's a tunnel that has been made through the mountain. Now, in quantum mechanics, here's the very weird thing. A particle may not have enough energy to go over the top of the mountain, but it can tunnel through the mountain. The mountain is a potential barrier. So what is a potential barrier? It's something that you need to cross. If you have enough energy, you can cross the barrier. But in the case of quantum mechanics, it's possible to get by even if you don't have enough energy. So coming to what I just talked about. So here is a particle that would normally come this way, and it would go up to, let's say, this maximum height, and at that point it would stop, and it would then roll back. So it would go up, and then it would go back. In quantum mechanics, what can happen is that you can violate the conservation of energy for a very small time, delta t. Now, if you can violate conservation of energy, that means some of the time this particle may be able to go through the barrier. It suddenly found energy and went over to the other side. Now, when it went over to the other side, it was moving at the same speed as it was earlier, which means that no energy was actually gained or lost. Let me repeat that. This particle came in with some kinetic energy and went out with the same kinetic energy. So potential here and here are the same. But for a short time, it was able to find energy to jump across the barrier. Very weird, but this is actually what happens. And how many examples could I give you? Well, the most beautiful example is that of an alpha particle which is bound inside a nucleus. And it rattles inside, and then sometime it finds the energy to jump across. So I've talked a little bit about quantum. I've talked a little bit about now quantum mechanics. I need to talk about quantum fields. And here is where the difference will become completely clear between classical and quantum fields. Okay, same example. Oops, sorry. I need to pull this down. Yeah. Same example as before. There's a string that is taut, a taut string tied at two ends. There's the equilibrium position over here. The equilibrium position is possible classically. Classically, there is no motion. You remember that ball could be at the bottom of the well without any motion. Well, here we have a string. Quantum mechanics says that no particle on that string, a string is made up of particles, remember, no particle on this string can be at rest. So there's no such thing as a string which is forever in equilibrium. Very, very strange. The uncertainty principle has made it necessary that the string forever be vibrating. Okay, now this actually becomes very, very practical. It becomes of great practical importance. Think of atoms that are in a crystal. Now, in a crystal, the crystal is very well ordered, so you have atoms joined to other atoms, And if you move one atom, then it'll want to come back to its original position, which means that there's a kind of a spring which joins it to the other atoms. Now, normally you would expect that these springs and balls would be at rest, but now Mr. Heisenberg says, no, 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 you can't do that. And so there are always going to be vibrations, even at 0 degrees Kelvin. At absolute zero, even then, there are going to be these vibrations which you simply cannot get rid of. Now here, suppose that I was to pick up one of these atoms and let it go. Well, the vibration would then propagate through the crystal, and it'll be a wave that'll go through, and that wave is called a phonon. If you want to think of a quantum field is something that is eternally in unrest, in motion. It's bubbling. Okay, now here is something that is really bizarre. And I'll pose it as a question. Now you might think that this is a very stupid question. Is the vacuum empty? Okay, so suppose I was to take out all the air from this room. Not easy, but you can imagine that I have a pump that takes out all the atoms that there are. Well, even if I do that, in the walls of this room, there are atoms. And those atoms, so you see, I have to, I'm in a box, and every box has to have walls. Those walls are made up of atoms, and inside those atoms, there are electrons. Now, suppose I was to even take those walls away, and so I'm located in space, far away from any possible kind of matter. So is that vacuum empty? And the answer is no. Here's why. Every particle that we know is made by combining waves. These waves are the waves of the field that belongs to that particle. So for example, the particle of light known as the photon is made of electromagnetic waves. Now the electromagnetic waves are fields, and they are quantum fields. And now you know that a quantum field can never be at rest because of the Heisenberg uncertainty principle. And so therefore, what happens is that for no reason other than the uncertainty principle, the vacuum is bubbling, it's oscillating. There are photons in it, but also there are other things, and I'm going to talk about particles and antiparticles very soon. There'll be particles and antiparticles in it, and in fact, the vacuum is extremely, extremely complicated. If we could understand what the vacuum truly is, we'd have solved most of the problems of the universe. But now, let me tell you how the idea of how the fact that a vacuum contains quantum fields can be actually measured. You see, in physics, we don't care if somebody has an idea as unless you can get observable consequences from that, it doesn't matter. Okay, so now this is called the Casimir effect. And I think this goes back to the 1940s. So here is the following situation. Normally, if you don't have, so this over here are metal plates. And this is also another metal plate. We have the capacity of being able to measure the force between these two plates. There's nothing in between them, in between these two plates. These plates are not connected to anything, so I could just actually remove this over here. It's just might be needed for the force measurement, but okay. So just two plain parallel plates. What Casimir predicted, and then this prediction was verified just a year or two or some time after that, he predicted that there'd be a force between these plates. And this force would come about because of the fluctuations of the quantum vacuum. So now let's backtrack a little bit. This vacuum has got photons which pop out and photons which then get destroyed. Now remember that delta E, delta T is H. And so for a very short time, photons, particles of light, will be created. That creation takes energy, right? Because light is energy. And you'll say, well, the photon just can't come into existence by itself because energy is needed for that. But yes, that energy is provided by the uncertainty principle. So you have photons that suddenly appear from nowhere and then disappear. So on the average, no energy is being violated. But for a short time, yes, energy is violated. That's what Heisenberg is saying. Okay. So this happens in space everywhere, all the time. What's so special about putting in these metal plates? Well, the metal plates, in a metal plate, you can't have an electric field. It would cause the electrons to move. And so the electric field here and the electric field here is zero. These are the boundary conditions. As a consequence of that, there's a difference between the energy of the vacuum in which there's nothing around and the energy of this vacuum in which there are plates. In consequence, there's an attraction between the plates. Now that attraction is very, very small. And that attractive force is proportional to h bar. I don't remember if it's h bar or h bar squared, but it's very, very small. No, h bar in fact, I think, yeah. That is very, very small, but it was measured. And it was measured 60, 70 years ago. Now in nanotechnology, we encounter the Casimir force even in things like micromotors, nanomaterials, nanomotors, that sort of thing. But the idea, look, is absolutely rooted in the idea of the uncertainty principle. Okay, so now let's move on. I want to take you on a quick tour of particle physics. And particle physics is about small things. Okay, so we take a plant and you look at it and there's a cell over there. You look inside the cell, you'll see molecules. You look inside the molecule, you'll see atoms. You look inside the atom, you see there's a nucleus. Here's the nucleus of the atom, and there's the electron. The electron is not only small, but it has no size. It's point-like. But inside the nucleus is made up of smaller elements. They're called quarks, and the quarks come in two different kinds, 6 actually, but inside the neutron and proton, they're the down quarks and the up quarks. Every particle that exists in the universe, so far as we know, every particle is made up of these 6 quarks, 2 of which we find in the neutron and proton, down, strange, charm. Called beauty, and this used to be called the truth quark, but now it's just called the T quark. You see, physicists, they have a very strange way of naming things. Anyway, so there are these 6 quarks. There are these particles called neutrinos. I don't have time to talk about them. There's the electron. There's the big brother of the electron. The still bigger brother, the biggest brother of this. So actually we have 3 families. These belong to 3 families of quarks and leptons. Then we have the photon. The photon is actually what causes charges to attract and repel each other. The gluon, which is the thing that holds quarks together. And then there are these 3 particles, the Z0 and the W plus and W minus, which were predicted by Abdusalam and Steven Weinberg back in their paper 1967, 1968. And there's one, so how many does that make? How many can you count over here? 4 plus 4 plus 4. Plus 5, because there's the W plus and the W minus, these. So that's 17 particles, and there's one which is called the Higgs boson, and I'm going to spend some time talking about that because it's what is called the God particle. Okay, briefly about matter and antimatter. Okay, so yeah, I should tell you. So this is way back in the 1920s, 1930. Okay, even before that, 1905, we have Einstein, who came up with E equals mc squared, which in a different form is this actually. E equals mc squared is only when a particle is at rest, but if it has momentum, then this is the right expression, the correct expression for the energy. If you take the square root of this, well, you get everybody knows that. But then, hang on, there's a negative energy over there too. And what does the negative energy mean? And especially, what does it mean when you try to combine Einstein's theory of relativity with quantum mechanics? And that was the great challenge in those days. And that's what led to a long series of developments, the Klein-Gordon equation, and then came along Paul Dirac, and he invented the Dirac equation. And the prediction, the theoretical prediction of the Dirac equation was that there would be such a thing as an antiparticle. You see, we, in our daily lives, we experience only particles. We experience the neutron, we experience the electron, the proton, the neutron. But what Dirac predicted from an analysis of his equation was that for every particle that exists in nature that we see, there is the antiparticle which has got everything else the same mass, the same spin, but it has the opposite charge. So if there's an electron, there's an anti-electron. If there's a proton, there's an antiproton. If there's a neutron, there's an anti-neutron, etc. So all of them. Well, sometimes a particle and its antiparticle can be the same, example being a photon. But in general, these will be different from each other. And if an electron and a positron, meaning an anti-electron, meet, then they're converted into light, into photons. It's a very bizarre idea that there should be antiparticles which annihilate on meeting particles. But you know, now this is not bizarre anymore. You can go to a hospital today and get, if you have cancer, I hope you don't, but you can get positron electron tomography. And this is really the bizarre and the wonderful thing about physics, is that something which is so far theoretical can get translated into something that is so eminently practical, to the point that it's there in your hospitals now. So anyway, coming back to this, for every particle there's a corresponding antiparticle. A particle is destroyed when it meets its partner antiparticle. And every particle, I've already stressed this, every particle has an associated quantum field. And it's that quantum field which is always bubbling, can never be zero. Antiparticles have their own field, particles have their own field. Sometimes these are, this is an example of how a neutron converts into a proton, and this is done through the field of the quark, the field of the W minus, and the field of the electron and the neutrino. So a neutron gets converted into a proton, and it doesn't take too long, 600 seconds. 600 seconds is what, 10 minutes? In 10 minutes, if I hold a neutron in my hand, it'll die. It'll disappear. Now, I'm going to come to the last part of my talk, and it'll be the Higgs field and what's called the God particle. Peter Higgs died yesterday. Well, here he is in 1964, and behind him is what is called the Lagrangian for the Higgs field that's written down. The particle that was predicted by Higgs, and I should say it wasn't just by Higgs, there were 5 other people, but 3 of them died, I think, earlier. Not so sure about that. Anyway, the whole reason that the Higgs particle could get discovered was because of Abdus Salam and Steven Weinberg. It was their theory of weak and electromagnetic interactions which told us that there is the W plus, there's the W minus, there's the Z0, and there is the Higgs. But the Higgs was very difficult to discover because it's so damned heavy. How they found it was by colliding protons at 14,000 GeV. Huge amount of energy. And that takes an accelerator that's 27 kilometers in diameter. It's in CERN. A huge number of particles per collision are involved, and okay. So basically it's this proton and this proton hitting each other, and then you see these particles coming out, and amongst those particles is a Higgs particle, and the Higgs was the last one of the 18 standard model particles to be discovered. It's got this stupid name called the God particle. And this is the name given by Leon Lederman. Lederman was the head of the theory group at Fermi Lab in Chicago. There are lots of jokes about it. So you can.
There's a joke, goddamn.
Yeah, it's also called the goddamn particle.
Yes. Clarify that no, it has got nothing to do with
Yes, no, it's got nothing to do that. Okay, there's a lot of hype about the Higgs particle, but really it's a quantum of the Higgs field. See, I keep insisting that it's the field which is important. The particle is just a lot of waves from that field joined up together. You see, that's why I showed you that animation in which you add up all those waves and you get a bunch. A bunch of waves is a particle. Waves of what? Waves of the corresponding field. Whether it's the Higgs, whether it's the electron, neutrino, quark, whatever. Now, why is this Higgs field, which is a scalar field, so important? Because every particle interacts with the Higgs field, and the particles which interact more are heavier, and the particles which don't interact at all remain massless. So the photon is massless, and the gluon is massless. So I have to tell you a little bit about this. Okay, now I move my hand around like this, right? I don't feel anything. Well, there is air, but if you took this air out, what would remain? The vacuum. Now, in this vacuum, there is actually the Higgs field. And this Higgs field is different from all the other fields in that it has a certain average value. If you ask what is the average value of the photon field, answer is 0. If you ask what's the average value of the electron field, 0. There's only one field which has an average value, and that's the Higgs field. The reason it can have an average value, actually we know what that average value is, we've measured it, is that it's a scalar field and it's not a vector field. Very, very important. See, if there was a vector field points in a certain direction. Vectors always have a direction. But if there was an average value to a vector field, that means our universe would be very different in this direction as compared to this direction as compared to that direction. The fact that our universe looks the same no matter whether you go this way or that way or up, down, whatever, is that there is no average value to any vector field. But there can be an average value to a scalar field. Yeah, but then what is it that gives the Higgs field an average value? I won't be able to describe that fully, but at least give you, another joke. American obesity. He says, the reason I'm so fat is it's not my fault, it's the Higgs fault, because it's the Higgs which gives mass to all the particles. Now, I just told you about the average value of the Higgs field, and if we were to put that average value equal to 0, we would be flying in the air today. All our neutrons wouldn't have any mass. So that's why it's called the God particle. It's the particle which gives mass to everything. Okay. Now, the reason the Higgs field comes about is of a phenomenon in physics that we call spontaneous symmetry breaking. And so, for example, an example of spontaneous symmetry breaking is, suppose that and balance it. Think of it as on your fingertip over here, you're balancing a pencil. Now it can fall this way or that way, and it can do so because there's no energy cost involved over here. It costs as much energy to tip over one way as another way. Theory which has rotational invariance, but the ground state, the lowest energy state, is not invariant. It falls one way or the other. Or let's take you have little magnets inside the material. If they all join up, then it becomes a magnet, and if they are in different directions, then you don't get any magnetism. Now, what happens is that for no good reason, they can all join up and point in this way, or equally well point another way. The symmetry is broken by some external factor, maybe a slight bit of wind, maybe a slight bit of magnetism, stray magnetism, whatever. And the Higgs particle and the Higgs field basically comes about because of spontaneous symmetry breaking. I can't explain any more at this point, but there's just one last thing that I have to tell you. And it's very important because it has to do with how our universe might end. Okay, so have a look at this, and now I'll tell you what actually is the case. So something like 13.7 billion years ago, the universe came into existence through a Big Bang. And of course, it was not in equilibrium then, but it could have reached a state. So if I was to think of the universe as having achieved an equilibrium after some time, I don't know how much time, well, it would have arrived over here, and it is very possible that this is where we are today. That the universe is in equilibrium, it is in its lowest energy state. On the other hand, there could be another energy state which is lower. And you remember when I talked about quantum mechanics and tunneling, so this is a potential barrier through which the universe can tunnel across and come to the true vacuum. So this is what we would call the false vacuum. False vacuum in what? Now it's the Higgs field that I'm talking about. The Higgs field, I can't explain too much, but the Higgs field has a potential. And if that potential looks like this, then that means the universe today is here, but at some later time, that later time could be tomorrow, or it could be 100 billion years from now. We don't know. I'll tell you what we know and we don't know. The universe could tunnel from the false vacuum to what we call the true vacuum. And now this is very much like what one has in a superheated liquid. Okay. Imagine that you've put a glass of water in a microwave oven, and it's heated up, and maybe its temperature has reached 103 degrees centigrade. Now it is not yet boiling, but the slightest disturbance will cause it to boil and in fact cause it to explode. And to go from the false vacuum is 103 degrees centigrade, to the true vacuum is steam. How does it do that? Through micro bubbles. Bubbles that are created but which get swallowed up by the liquid until they reach a critical size, and when they reach that critical size, then there's a transition from the false vacuum to the true vacuum, from the superheated liquid to steam, from the universe here to the universe here. So for all that we know, the universe could end tomorrow. The good news is you won't even know about it, because the time taken, the disturbance will move. The walls of the bubble will move at the speed of light. And so this was a calculation that was done in 1980 by Sidney Coleman at Harvard. I wish I had paid more attention to it then, but now I'm trying to understand his work and finding it fascinating. So I think we're out of time, and now time for questions. Okay, so folks, let's have questions from your end, and then we'll have questions from this end as well. I know you have an agenda, you have other things to do today, so let's have your questions. We need your questions.
Yes, hi. Just a confirmation of the graph you have on the chalkboard.
Yeah.
What would you define the axes as?
So this is the Higgs field, and it's sort of symbolic, okay? But it's this phi over here signifies the Higgs field. The Higgs field, of course, is different at different points in space-time, but at any one point in space-time, it would look like this. In fact, we can calculate this potential in quantum field theory, and yeah, people are still working very hard on that. There have been about something like 3,000 papers on the fate of the false vacuum.
Another question we have, when you're going from the false vacuum to the true vacuum, what type of energy would be required?
Well, whatever difference in energy there is between here and here will be released in the form of heat. And this is one way by which the universe could be reheated. I should also tell you that, see, the Higgs field here and the Higgs field here are different, which means that if we should make a transition to the true vacuum, then everything is going to change. Chemistry will be totally different. You won't have you won't have hydrogen bonding to oxygen, for example. We can't calculate what the new universe would look like, but it's extremely unlikely that it would be able to sustain life.
So would Planck's constant also change?
Would Planck's constant also change? No, not Planck's constant. Look, these calculations are done with a fixed Planck's constant, a fixed value for the fine structure constant, speed of light, alpha squared, alpha squared, which is h bar over mc. The gravitational constant would not change. But the change in the Higgs field would then change all the masses of all the particles. I said something wrong. Alpha squared is E squared over h bar c. Okay.
We have one more, I think.
Okay.
Okay, so you were explaining about the E given by P square over 2m plus 1/2 kx square. What is K and what is the effect on energy?
Sorry, about the
Yeah, your energy formula
Yeah.
with the value of K.
okay. Well, when I said this, p squared over 2m plus half kx squared, so I was actually, I should have actually said that this is a spring and a mass, but exactly the same thing holds over here. So here the potential energy will, here I meant really that V as a function of x is something that goes as x squared, and it would not be a gravitational potential. It would be, it could be, but it doesn't have to be. So I think this is something that one should be thinking of: p squared over 2m plus half kx squared, a spring and a mass.
Thank you. And what about the questions in your room?
Let's have questions over here in this room. Yeah, there's a question here.
Thank you. I was just wondering, you have this graph which is showing something like you go from false vacuum to true vacuum. Is it something, I guess it is somehow showing that the universe is expanding? at some point, and then it is contracting, and then there is going to be, contracting is going to be so much that it's going to collapse eventually?
No. It's not that. Okay, it's really how the Higgs field changes from the false vacuum to the true vacuum. Now, if the Higgs field changes, then all the masses of the particles change. The question you are asking is, how will the geometry of the universe change? Because we live in a world that where the geometry is determined by the matter. And that's a complicated question. People have worked that out. And what they find is that if you go from the false to the true vacuum, then the geometry doesn't change under most assumptions. So, things will keep spreading out. In fact, as we see it today, the universe is not only expanding, but it's accelerating as it expands. And that is not likely to change, or at least change very much.
So the Higgs field doesn't change with the expanding universe?
No, the Higgs field doesn't change with that. And in fact, after the first microseconds, there has been no change in any of the fundamental constants.
Okay, and I've been listening that the laws of the universe, they do not match with the laws which are defined in quantum mechanics.
No.
How we can relate this stuff with the universes?
The laws of physics do not change, or at least have not changed in the entire history of the universe. In fact, if you look at the light that comes from the distant stars, the spectrum of light is exactly the same as we find on Earth, which means that billions of years earlier, when that light was emitted, it was emitted according to the same laws of physics as exist today on Earth over here. So that's not changed. Yes, sir. Next.
Doctor, I would like to know
You have to keep the mic closer.
I would like to know the difference between the false vacuum and the true vacuum. The life existing at the moment, you mean to say that it is in the false vacuum? And how would we move to the true vacuum? Is it through a process of transformation, or it will be abrupt? And the quality of life, when you say false vacuum, what do you mean exactly by false vacuum, and what do you mean exactly by the true vacuum?
So what I mean by the false vacuum is strictly in the sense of physics, which is this. So this is a minimum, so is this a minimum, so is this a minimum, so is this a minimum. However, this one is lower than all the other minima. And so if one starts, for example, over here, ultimately one will reach the lowest energy. But how long will it take? It depends upon the system. I'm speaking from the point of view of pure physics. In the case of the universe, well, to conceive of the universe as having originated in a potential which was made possible by the Higgs field, how long it will take to get from where it is presently to where it will be later, you can do a calculation, but you can't predict what that new universe will look like, because we don't know what will be the values of the what will be the masses there.
like to further clarify, what I would like to further clarify, that you have said that we go to the lowest edge in the true vacuum. So, what do you mean exactly by true vacuum? That the quality of life?
No, it's got nothing to do with
Nothing to do
quality
with-
of life. It's
But the universe is taking a shift according to your theory. or
it's
whatever
not
it
my
is from-
theory. It's
what-
I wish
according
it
to the
was my
that you
theory.
have
But
reflected.
this is
No, the theory of the physics, the false vacuum traveling, which may take years together, centuries together.
okay.
as you
Maybe
said
we can
earlier.
talk about this later.
But once we go, you say that we go down the lowest ebb, and that is the true vacuum.
It's the lowest energy state. One wants to come down
Once
to
we
the.
go to the lowest energy state, and why do you call it a true vacuum?
That's by definition.
I would like to
That's by definition.
like
let's
to perceive
let's
exactly as to what do you mean.
lowest
by
energy
exactly
state.
Lowest energy
State.
state is the
True vacuum is the true
Why?
vacuum. Correct. Okay.
You said that in the true vacuum, the Planck's constant and the fine structure constant, etc., will remain the same. Is that an assumption, or what reason is there to believe that they will remain unchanged?
Let's start from the a priori observation that in the far past we have certain values for the fundamental constants of nature, which is E squared, which is the charge on the electron, h bar, speed of light, gravitational constant, 4 of these, right? There is no a priori reason for assuming that they will be different tomorrow. And so therefore that is a conservative, that's a conservative approach. It's the natural approach to take. And so that's why we say it'll be the same tomorrow as it is today.
So, will it be the same universe that goes into the true vacuum, or will it be a different universe? It will obviously be different if the Higgs field is different.
Yeah, well, let me say, suppose we have this situation. Suppose we have a situation where the difference between the two is very, very small. In that case, we will have gone from the false to the true vacuum, but the difference in the mass of the electron or the mass of the quark will be small.
No, but
So-
the difference is along the x-axis. That could be large. So the Higgs field could be
No,
very
no,
different.
no. This is the difference in energy.
In energy, yes,
In
but the
difference
Higgs
in the
field.
Higgs field. The Higgs field here and here will be approximately the same.
No, but the Higgs field is on the x-axis. And
Yes.
if the two minima are far apart, then the difference in the Higgs field will be large. Not far apart in energy,
No,
but
this
far
is-
apart along the horizontal axis.
That is correct. So then I should do the following. I should take these as close to each other. Okay, so then the difference in the Higgs field will be small.
That's only visually small.
So the world you wake up in tomorrow will not be very different from
But
today.
it is also about that a universe that we are living today is going to die, and a new universe is going to be created. And in that new universe, we would have some different Higgs values as a scalar field. It's a scalar field, so we'll have the average value would be a bit different. And the vacuum, you mean to say that since we don't have Higgs field, so particles wouldn't have any mass, and that's why there would be a vacuum.
see, it's going from one vacuum to the other. The qualities of those vacuums, of those different vacua, would be characterized, of course, by the value of the Higgs field, but also, in terms of then the different ways in which particles would behave with respect to each other. So I can't make any prediction of what that new universe is going to look like.
Sir, you said that the Planck constant does not change. So suppose if the Planck constant change, then would all the fields would change or not? The vector field, scalar field, etc.
Well, look, there is no reason to believe the Planck's constant will change. You can equally say what will happen if the charge on if the fundamental charge changes, if the gravitational constant changes, if this changes, that changes. Everything will change if you change any of these fundamental constants of nature.
Small question about Planck's constant.
Hello, sir. We discussed many particles and mediators also, but I think we missed the gravitons. Although it's not any work with standard model, but is this just assumption or any reality with it? Thank you.
Yes, thank you. That's a good question. So if we have two charges, plus minus or plus plus whatever, in between them goes the photon denoted by gamma, and it goes back and forth, and it's what leads to the force between them. If we take one mass and take another mass, then what is the thing that goes between them and causes attraction? That is the graviton. But the reason we don't talk about gravitons very much is because they're very hard to detect individually. Individually, we can detect photons. Individually, today, we can produce single photons. We study their properties, everything about that. But gravitons so far have not been detected. The reason is that if we take two bodies, then a very large number of gravitons go back and forth. And you can have such a thing as a gravitational wave, but a gravitational wave behaves classically. It doesn't behave quantum mechanically. For the quantum mechanical aspects of a field to be apparent, you need to have great sensitivity, and in terms of gravity, we don't have that sensitivity.
Is the Big Bang was a transition from some false vacuum to current vacuum, or once transition happen, it will always go to the global minimum?
Okay, so we don't know, and in fact, the first paper that was written by Sidney Coleman, and he said flat out at the beginning that I am going to treat this as a theoretical problem. It is very possible that we are not in this false vacuum, but that we have already made the transition to the true vacuum. Maybe. If so, then we are okay. But what if this curve turns over and there's something lower? Then these could tunnel across over here. But maybe the curve doesn't look like this. Maybe it'll keep going up. So in that case, we would be okay. these ideas of the universe are not so easily checkable, but the idea of quantum tunneling is something that we use now to, you've heard of the electron microscope, the one with the needle, what's that called? The scanning electron microscope. That works on the principle of tunneling, and tunneling is something that you can see, the tunneling electron microscope. Tunneling electron microscope, we see bumps in the atoms as we go across the surface. So the ideas are very strong, and then it's a big jump to whether and in what way they apply to the universe at large. Okay, I think we're done with questions, or one last question? Okay.
I have two questions.
Okay.
First, a continuing question. As the scanning electron microscope works because of this tunneling effect, and now we're also talking about some statistical chances that there's going to be a transition from one vacuum to another.
Yeah.
How this can happen if the scanning electron microscope works? What is the probability that this can actually happen over the whole Higgs fabric?
No, that's an unanswerable question. We don't know when the end of the universe is.
No.
But
Statistically, we can estimate. And
no. What we can estimate, okay. So there is the standard model of particle physics. The question we can ask is, are we at a critical point or not? And the answer to that depends upon how well we can measure the mass of the Higgs boson. As of the present time, that mass has not been measured well enough. It needs to be measured 10 times better. In which case, we will be able to say, are we going to fall into a deeper ditch? That is a question that can be answered. What cannot be answered is, how long will it take? This is a probabilistic analysis.
Yeah.
You can calculate transition probabilities per unit time, but beyond that, no.
very simple, small question. Maybe my last question.
You can say he's okay
This,
with doing that. He's okay.
Sorry to interrupt. We have to sign off. So thank you, Dr. Hoodbhoy, for your presentation, and it was great to interact with two rooms. Thank you for your time.
Thank you. Okay, good. Bye-bye.
Okay, see you.
Huh.
The last small question.
Yeah.
Probably the answer is not that simple. I just wanted to know that this Planck's constant, no matter the number is very small, how this was calculated or it was measured?
Measured. देखिए, उसमें ये अब हम
What was the process?
अपनी मर्जी से बात कर सकते हैं. तो प्लैंक्स कांस्टेंट की बात कहाँ से आई थी? E is equal to h nu. ये एक इलेक्ट्रोमैग्नेटिक वेव है जिसकी फ्रीक्वेंसी न्यू है. h वो नंबर है जिससे हमें उस वेव की एनर्जी मिलती है, उस पार्टिकल की एनर्जी मिलती है. हमें कैसे पता चला कि हर फोटोन की एक मखसूस एनर्जी है? फोटो इलेक्ट्रिक इफेक्ट से. फोटो इलेक्ट्रिक इफेक्ट में ये था कि आप रेडिएशन डालें इस ऑब्जेक्ट, इस टारगेट के ऊपर, कोई इलेक्ट्रॉन्स इससे नहीं निकलते उस वक्त हैं जब ये फ्रीक्वेंसी न्यू एक हद से ज़्यादा हो जाती है. उससे जब तजावज़ करती है तो इस फोटोन की एनर्जी इतनी हो जाती है कि उस इलेक्ट्रॉन को वो निकाल कर बाहर फेंक सके। ये प्लैंक्स हाइपोथेसिस कहलाता था 1904-5 उसके लगभग, और क्वांटम मैकेनिक्स की शुरुआत यहां से हुई थी। ओके, ओके, गुड।